Good morning, Algebra 2. Let's get going with Unit 2 Notes Day 4. Read through that stuff. Maybe once we're done with notes, maybe it'll make a little bit more sense at that point. A relation can be represented in the following ways: ordered pairs, table, graph, mapping diagram. Now, this is the same relation, just written differently. As you notice here, we have the ordered pair. Now, you probably know by now that in order for a set of ordered pair to be a function, the x value cannot repeat. Notice that the x value is repeating here and that it is producing a different y value. No, that can't happen. That is not a function. Neither of these are functions, simply because the x values repeat, if you will. But these are just different ways that the information could be presented, yet they all mean the same thing. Is the relation a function? No. Now, what is the domain and range of the function? Domain. Those are all the x values. Range. Those are all the y values. Right here, if you want to write vertical and 1 point. Vertical line test. A relation is a function if and only if no vertical line intersects the graph of the relation at more than 1 point. This function, if we were to conduct a vertical line test, just drawing vertical lines, see how many times does it cross our graph? Well, here it crossed once, here it crossed once, there once, there's, that one's fine, that's a function. This one would not be a function. It doesn't pass the vertical line test because it crosses our graph once, twice, not a function. Part 4, use the vertical line test to determine if the relations below are functions. Take about 5 seconds and do that. And if you perform the vertical line test correctly, those would be your final answers. Let's move on to side 2. Right now would be a really good time to pause the video and start filling in some of these blanks. All right, this next section here, identify whether the following functions are linear and explain why, and then evaluate the function as indicated. This one here, if you divided both sides by 4, that would leave us with y equals 3 over 4x. So yes, that is linear. Anything that is linear can be written in the form y equals mx plus b. Now this one is not linear because you see that exponent of 2 right there? That's actually quadratic. We'll be working with those a lot this year. This one, is this linear? No. You see that exponent of 3 right there? That's cubic. We'll be doing some of those also. And then this one also, no. You cannot have x in the denominator. All right, next, let's evaluate these functions. So they want us to take, if x equals 12, substitute it here for x, and then solve for y. So we want to take 4y equals 3 times x, but instead of x, substitute 12. That's what I want you to do. And then solve for y. That's your answer for that one. Okay, next, find f of -3. That means given this function, watch what I'm about to do here. The function is 2x squared plus 4x minus 1, but watch what I'm going to do. I wrote the problem, except instead of x's, I opened up a set of parentheses. And in those parentheses, we're going to substitute -3. And then we start solving. -3 times -3 is +9. 4 times -3, that's -12. Carry down the -1. Distribute 2 times 9, 18. 18 minus 12. That's 6. 6 minus 1, 5. That's our answer for that one. Okay, here. Find g of -1. So here's that function, x minus 2 times x cubed. Notice I'm not plugging in a g of x, by the way. G of x, f of x, f of x. You could think of that as y. We don't want to plug anything in there. So x minus 2x cubed. Instead of x, I wrote parentheses, and in those parentheses, substitute -1. Well, here these parentheses aren't really needed. Now, -1 cubed is the same thing as -1 times -1 times -1, which is -1. And now distribute -2 times -1. And now we can combine these like terms. That's your final answer. And then the last one, find f of 1. I think I have it right below this. So 2 over x plus 3. In those parentheses, let me substitute 1. The parentheses are not needed any longer. Now I can simplify that denominator. 1 plus 3, that's 4. And then reduce. That's your final answer. Okay, absolute value parent function. Make a table of values, vertex, and then it gives you this table here. This is, by the way, this is the parent function of absolute value functions. Y equals the absolute value of x, and it wants us to graph that function. Here's what I'm going to do. I'm going to start by putting a coordinate right at the origin. And now from the origin, I'm going to go up 1, right 1, and put a dot. Up 1, right 1, put a dot. Up 1, right 1, up 1, right 1. I'm going to continue that pattern as if the slope was x, or as if the slope was 1. Now, go back to the origin, and this time go up 1, left 1, up 1, left 1, up 1, left 1. Absolute value. Absolute value functions, they produce V shapes. We can connect these dots. Now, the vertex is the starting point, if you will. Didn't I start at the origin? That coordinate, the origin, is 0, 0. That is our vertex. From the vertex, our graph then opened up. It has a table here that it wants you to use, but I'm not going to use that actually. I actually think there's a easier way of graphing absolute value functions. Using a parent table will come in handy, but I think this unit, let me show you a different method. Let's move on to the next side. Make sure and in that blank there, put vertex. Now it wants us to graph y equals the absolute value of x minus 2. Now, originally, our graph started at the vertex. But do you see that minus 2 that's to the right of the absolute value? That means from the vertex, our graph is going to shift down 2 units. So this is where our vertex begins this time. 0, -2. Now, do you remember when we graphed the very first function? Where I started from? I went up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Remember that? And then I went back to where we started and did up 1, left 1, up 1, left 1, up 1, left 1. That trick will work here. And I'm going to point out why in just a moment. All right, this is an absolute value function, produces V shapes. If you think of it though as just a linear function, y equals, let me drop the absolute value. Actually, I don't like that. I've changed my mind. Don't look at it that way. That's normally not the way I teach it. And I was having a grand idea, and then I realized that's not actually going to work every time. But here's another way. Let me write down what that function is one more time. Y equals absolute value of x minus 2. Look in front of x. Right in front of x. There's a number there. You can't see it. The number is 1. If you pretend like your slope, if you will, and now this isn't absolutely correct, but it will help. If you pretend that your slope is 1, that's how you're going to plot every other dot. That's what I did. Up one, right one, up one, right one, up one, pretending the slope is 1. But then you got to remember, when you go back to the vertex, since it's not linear, you don't want to continue that pattern this direction. You want to continue that pattern the other direction. If you wanted to then fill in these tables, you could. Let's start with our vertex at 0, -2. And then use a couple of numbers before and after where x is 0. Looks like when x is 1, y is -1. When x is 2, y is 0. When x is -1, y is -1. When x is -2, y is 0. X-intercepts, hey, guess what? We just plotted them. You can look on the table here that we created, or the graph. Our x-intercepts are -2, 0, and 2, 0. Our y-intercept, there it is right there. It also happens to be our vertex. Won't always happen that way. Domain. Domain means if your graph were to continue going forever, how many x values would it cover? Well, since it starts here and it's going to continue opening left and right forever, it's going to hit every x value into -infinity and +infinity. So that's your domain. Left to right, we're covering everything from -infinity to +infinity. Range means what are the y values that this graph covers from bottom to top? Now it starts at -2, and it includes -2, so give it a bracket, and then from -2, it's going to cover every y value to +infinity. What transformation occurred from the parent function? We went down twice. Down 2. Example B. If I were to look at this function, here's what it's going to do. You see the x plus 3 in the absolute value. This is the first time we've had a number in the absolute value with the x. Here's what it's going to do to your graph. Remember, the parent function starts at the origin. This graph is going to shift 3 spaces to the left. This is where our graph begins. So the vertex is now -3, 0. You may be asking, how are we shifting left 3 if we have x plus 3 in parentheses? Well, what you're supposed to do, I meant absolute value, is you're supposed to set whatever's inside the absolute value equal to 0 itself. Meaning x equals -3. So from the origin go left 3. That's why we went left 3. Okay, now look in front of x. Look in front of x. Do you see a negative? No. Do you see any other number? No. So we can pretend our slope is 1 yet again. So from the starting point, from our vertex, go up 1, right 1, up 1, right 1, up 1, right 1. Go back to our vertex. This time go up 1, left 1, up 1, left 1, up 1, left 1. Connect. X-intercepts, well, we can tell by looking at the graph. We have 1. Y-intercepts. Looks like we come in contact with the y-axis right there. It's at 0, 3. Domain, still -infinity, +infinity, which is going to be the case for all absolute value functions. And then range from bottom to top. We cover all y values from where y is 0 to positive infinity. What transformation occurred from the parent function? Well, from the origin, we went left 3 units. Example C. Here's how this one is going to change from the parent function. If you set x minus 1 equal to 0 and solve, you'd get x equals negative, or x equals positive 1. My bad. Sorry about that. Positive 1. So from the origin, this graph is going to go right once. That's our starting point. That's our vertex. 1, 0. Now, how are we going to plot all of our other dots? Well, look in front of x. I highlighted it. It's a dark highlighter, so it's kind of hard to see. There's a 2 in front of the x. So you could pretend that the slope, if you will, is 2 or 2 over 1. So from the vertex, go up to right 1, up to right 1, up to right 1. Go back to the vertex. This time go up to left 1. Now let's start answering these blanks. Our x-intercept, there it is right there. 1, 0. Y-intercept, there it is. 0, 2. Domain. Everything from negative infinity to positive infinity. Range from bottom to top. 0 to infinity. All right, now what transformations occurred from the parent function? You remember that 2 that was in front of our x? That is a stretch of 2. And from the origin, we went right 1. And then example D, last one, you're doing great, Algebra 2. If we are looking at this function here, we have a negative in front of our x, but there's nothing inside the absolute value other than x. Outside of the absolute value to the right, we have plus 4. So here is where our vertex is going to be. Starting at the origin, go up 4. 1, 2, 3, 4. That's our starting point. That's our vertex. 0, 4. Now, how are we going to plot all of our other dots? Look in front of x. We have a negative in front of x. So you could pretend your slope is negative 1. From the vertex, down 1, right 1, down 1, right 1, down 1, right 1. Go back to the vertex. Now do down 1, left 1, down 1, left 1. And then connect. Now let's answer these questions. Our x-intercept, looks like we have 1 there, where x is -1, -2, -3, -4. And 1 there, where x is positive 4. -4, 0, and 4, 0. Our y-intercept, there it is. 0, 4. Domain, hopefully you got this down by now. And our range from bottom to top. Now this is going to continue going forever. So from bottom to top, we want to start with negative infinity, and then we max out at 4. What transformation occurred from the parent functions? Well, let's start with the negative in front of the x, in front of the absolute value. I'm not going to write all this out, it's a lot, but that's what we refer to as a reflection over the x-axis. Reflection over the x-axis sits upside down. What it pretty much means. And then we went up, over. And that's it. Good job, Algebra 2.